Hey guys, welcome to this video. Another shouts out to all those AP Calc students cramming for the AP exam tomorrow. I wanted to give you yet another awesome, cleverly put together question by Bryan Passwater, and this is a different AB1, okay? So let's go ahead and begin. We are given the function f. It says the function f is twice differentiable for x is greater than or equal to 1, where f of 5 is equal to -6. So then it says selected values of the positive and decreasing function of what you have up here of f prime, so it's positive and decreasing, the derivative of f are given in the table above. So the graph of f prime also has a horizontal tangent at y is equal to 0, okay, meaning it won't go necessarily into the negative, it'll always stay that positive and yet still decreasing. So now we're asked to find what is the approximation, okay, so there's an average rate of change interpretation at 2.5. So we want to know at 2.5, which is somewhere around here, what's the approximate f double prime? Well, we know that f prime of x is, so per mean value theorem, if you will, that f prime of c is equal to f of b minus f of a over b minus a. Well, this also happens to be true for f double prime of c, is that difference quotient between f prime of b minus f prime of a over b minus a. And that's what's going on here. We are given this second derivative here that we're evaluating at 2.5. So we need a point to the left and a point to the right so that we get our f of b, which in this case, we're going to go ahead and write as 20 minus 30 over 3 minus 2. Okay, and this is going to be our f double prime approximation that exists halfway between 2 and 3 at 2.5. Okay, so again, 20 minus 30 over 3 minus 2. So let's go ahead and see. We get negative 10 over 1. So f double prime at 2.5 is equal to a negative 10. So that's easy enough, right? So now what we're going to do is we're going to go and look at, that's f prime of x. I just want to make sure I keep that highlighted. We're going to go and look at part B. It says use a right Riemann sum with 4 subintervals. This is again a right Riemann sum, and we're going to use it to approximate what is f of 1. Okay, we know what f of 5 is. F of 5 is -6, but we need to find f of 1. So this is another clever question put together that we're going to use first fundamental theorem. So the first fundamental theorem we're going to use is that, again, in this case, from 1 to 5, so let me go ahead and write from a to b, f prime of x in respect to x is the change in position f of b minus f of a. Well, in this case, I'm going to deem 1 as my a and 5 as my b because I want to integrate low to high. Oops, didn't mean to erase. So I want to integrate low to high. So I'm going to say from 1 to 5 underneath the f prime of x in respect to x will equal f of 5, which we're going to go ahead and just write in the -6, minus f of a, which in this case is f of 1. Now remember, f of 1 is what we are looking for in this problem, okay? So I can, if I want, rewrite it so that f of 1 is all by itself on the left side. And it's going to equal -6 minus, I'm going to go ahead and move this integral over to the right side. Oops. Make this a little bit neater. So we're going to say that f of 1 is equal to -6 minus 1 to 5 underneath f prime of x. Now, to find this right Riemann sum with 4 subintervals, we're going to use this piece right here. Okay, so this piece right here is like setting it up as the right Riemann sums with sub 4, because there's 4 of them. So I'll have 4, if you will, pieces of base times height. Okay, so I'm going to go ahead and write that over here on scratch work as -1 to 5 f prime of x in respect to x is equal to these 4 that I need. Okay, so if I have 4, 1, 2, 3, 4, you see that all of these widths, these jumps, if you will, the widths of each of these is going to just be 1. So we'll call that the base. So base times height plus base times height. And they're all 1. I don't have to write it, but I'm just going to write it just to a little bit, just show you that base times height. Now, Since I'm looking at the right Riemann sum, the first rectangle, this right height is 30. The second one is 20. The third height would be 15. And the fourth height is going to be 12. Okay? Again, we are looking at these as y values per se. So we have 30, we have 20, we have 15, and we have 12. So adding them all up together, we have 30 plus 20, plus 15 plus 12. We're going to get 77. 77 is this area right here in blue. Okay, so let me go ahead and highlight. Let me move that out of the way. This is going to be 77, so it's -6 minus 77, or 77. It'll be f of 1 is equal to a -83. Okay, let me not box that. So again, -6, so we're going to say a -6 minus that answer that we got before. You see that we got a -83. Now, this -83 is representing f of 1. And the question is it an under or an over approximation with this f of 1 being -83? Well, let's look at what we were given originally up here with this f prime of x graph. It said that not only is it positive, but it was decreasing, okay? So imagine this function is decreasing. It has this horizontal asymptote at y is equal to 0. So from 1 to 5, it's decreasing, if you will. Let's say this is 1, this is 5. This is just a quick sketch. If I did right Riemann sums, it obviously is going to be an under approximation. But we can't say that. We can't say because of the graph. Okay, we can never give justification or reasons for our answers by graphs like that. So we're going to say specifically that this is an under approximation. And the reason why is because f prime of x, which was this graph here and here, okay? And I'm talking about, let me highlight it in green the way I chose at the beginning. F prime of x is decreasing. Because you're doing a right Riemann sum and because f prime is decreasing, it will automatically be an under approximation. Okay, so look at all the pieces that we use. First fundamental theorem, we use the Riemann sum, all that justification, please make sure you list them all out. Let's go to part C. Part C, we know that we're going to take the antiderivative of f double prime of this stuff right here. Now, we can't integrate this stuff until this is one variable with a +1 coefficient. So already we know we're going to have a u substitution trying to get that parentheses piece to just be one variable with a positive coefficient of 1 that we're going to call u. Okay, so the differential is going to be a -3 dx, so that this integral's rewrite is a -1/3 du, and it's f double prime of u. Now, we have to look at our limits of integration. From -1, let's plug that in here. So we'll get 1 plus 3 is 4. And then we'll plug in this 0, again, right here, so that we'll get just 1. Now, I normally like to tell my students, especially when they're looking at graphs, to have this low to high. So just out of force of habit, I'm going to go ahead and flip those. And when I flip those, it will be from 1 to 4. But we have to account with the negative. That will multiply with this negative, becoming a +1/3. Everything else stays the same. It's just the rewrite. So f double prime of u du. And now I'm ready to integrate because I have this letter, this variable, if you will, with a +1 coefficient. The antiderivative of f double prime of u is just f prime of u. We will evaluate this from 1 to 4. And then we will constant multiple rule that 1/3 at the very end. So let's see, what is f prime at 4, subtracting f prime at 1, and then we will multiply this by this constant of 1/3. Okay, so f prime at 4 is 15. F prime at 1 is 62. So we're going to say 15 minus 62, and then divide by 3. So 15 minus 62, and then we're going to divide it by 3. It's just a -47/3. Okay, so this is going to be a -47/3. All right. So now let's go ahead and go to part D. Part D is a very, very clever question. I love this question. Okay, this part. It says, explain why there must be a time C in between 1 and 5, where f double prime of C is -4. Now we know mean value theorem that f prime of C is equal to this difference quotient between the positions. And that means f prime of C, that is. F double prime is also the difference quotient, but between f primes. Because remember, these are one derivative jump away from each other. Okay? So what this is saying is, we're trying to put this -4 as far as being equal to this. Okay? Now, let's look and evaluate what is f prime of 5. That's my B term. Minus f prime at 1 over 5 minus 1. Okay, let's see what this gives us as far as an average rate of change between our endpoints, if you will. So f prime of 5, I'm going to go up here, and f prime of 5 is 12. So we'll have 12 minus f prime of 1 is 62, and it's going to be over 5 minus 1. Okay, all this is over this f double prime of C. Now this is basic mean value theorem. Okay, so let me come over here. I'm going to go ahead and do 12 minus 62 over 5 minus 1. And we get -25 halves. Okay, so -25 halves is what this is. So -25 halves is like -12.5. Well, notice I didn't get this -4 that they're asking me for, okay? I didn't get this -25 to match up with the -4. But I do know that this is the average rate of change between my endpoints located at 1 and 5, which is up here and here, okay? So this average rate of change, this slope, if you will, between the endpoints is a -25 halves. And I want to see, is there a C value in between 1 and 5 where I will have a slope, if you will, of this f prime of x graph that you see here in green, where it's going to be a -4. Well, there's a way that we can do this by analyzing its endpoints, okay? A little bit carefully and seeing how can we use intermediate value theorem to also show that. Okay, so first of all, I kind of skipped over a little bit. There are two stipulations for mean value theorem. The first is the function continuous and is the function differentiable on the certain domain? Okay, so for this one per se, we're going to say f prime of x, because we're looking at the right side of the equation, if you will, is continuous, and we're going to say from 1 to 5. So is continuous on 1 to 5. Now, we're also saying f prime of x is differentiable, and it's on 1 to 5 in between the endpoints. We know that these two are true. That gives us the therefore this mean value theorem part here, because it was stated that f is twice differentiable. That means f is twice differentiable and twice continuous. So with that being said, that's how we know that it's going to be continuous and differentiable at its value or its level, if you will, the derivative of f prime of x. So now let's look at the intermediate value theorem. Our intermediate value theorem, we're going to go ahead and incorporate, and this is why I like this question so much, is we know that this -25 halves doesn't match -4. But look what I'm going to do. I'm going to say that if I were to do an average rate of change between these two, and then do an average rate of change between these two, then I can use the intermediate value theorem if -4 lies in between whatever these slopes are. Okay, so let's look at 30 minus 62 over 2 minus 1. That was the one in blue. The other one is 12 minus 15 over 5 minus 4. Okay, so this is a -3, and 30 minus 62. Oops, 30 minus 62, and I'm realizing I didn't go back, and I so apologize for that, is a -32. So negative 32 is going to be right here, and a negative 3. So again, and I apologize for not going back to this screen just now, but this right here is what I was talking about. The intermediate value theorem I'm analyzing is going to be between this and this point and these points over here. So what's circled in red came out to be a negative 3. What's circled in blue came out to be a negative 32. Okay, so with that in mind, I'm showing that if these are f double primes, this is f double prime at the very beginning between those 2 points, right? You could say f double prime of 1.5. And the last one was f double prime at 4.5. Well, we know by intermediate value theorem, the conditions are very close to what they are for mean value theorem. The only difference is that there's a third condition. So first condition, we're going to say f prime is still continuous on 1 to 5. We're going to say that f prime is differentiable on 1 to 5 non-inclusive. And then intermediate value theorem says, does the third one hold true? Does f prime at 5 not equal f prime at 1? Well, you know f prime at 5 was 12, okay? And we know that f prime at 1 was 62. But that's not what we're doing here. We're actually using this cleverly built question as far as not f prime of 5. We're looking at what did we look for here as far as those slopes are concerned. The slope meaning what does it exist here at 1.5 and what did it exist here at 4.5. Okay, so over here we can use something like at 1.5, was it different than what it was at 4.5? Well, we know at 1.5 it was negative 32, and that's not equal to negative 3. And now the last part, our k value. Let k equal negative 4. And k is in between this negative 32 and negative 3. K is in between. Therefore, since k is in between those y values, there must, and this is per intermediate value theorem, there must exist, in this case, a c value on basically between 1.5 and 4.5, non-inclusive, where f double prime, because that's what we're looking for over here, and again, the stipulations we're looking at f primes, but using this intermediate value theorem, we're going to go to the f double prime interpretation, where f double prime of c would in fact equal negative 4. Okay, so that's how we're going to determine that. There's a lot of cool stuff built on top of each other there in part D. Now, let's go to part E. Again, I apologize for not going back, but if you need to kind of rewind the video and pause it just to make sure that you understood what I was doing here at the intermediate value theorem, please do so, okay? Again, I do apologize for not changing that slide over. Part E, it says, write an equation for the line tangent to f at x is equal to 5. This one's a lot easier than part D. So x is equal to 5, that's like our a value, if you will, okay? So we're going to go ahead and plug that here so that it's x minus 5. Now I'm going to find what's the derivative at 5 on f and what's f of 5. Well, f of 5 was already given to us as a negative 6. That was our initial condition. So y minus a negative 6 is y plus 6. And now I just have to find out what is f prime at 5. Okay, so f prime, I'm going to go to the chart, and f prime at 5 is 12. Okay, so I'm going to go ahead and put 12 right here. And now what I'm going to do is I'm going to plug in, because I'm going to use this equation in the tangent line to approximate what would 5.1 give us. Okay, and yes, you could do this by hand or you can use a calculator. We'll say that y is equal to 12, in this case, 5.1 minus 5, because I'm going to plug in my x value of 5.1. And then I'm going to move this 6 over by subtracting it over, and then I'm done. So it's going to be something like, let me go ahead and use the calculator just for the sake of speed. So 12 times 5.1 minus 5, so that's 0.1, so that's 1.2. And then we're going to minus 6, so answer minus 6, we're going to get a negative 4.8. So y is equal to negative 4.8, or you could say f of 5.1 is equal to a negative 4.8. All right, guys. Oops, let me come over here and write that in. You could say y is equal to negative 4.8, or f of 5.1 is equal to negative 4.8. Hope you guys enjoy this question.